Okay, page 9 of the scheduling notes, and section 3, I forget what it's about. It's about concurrent execution, and section 3.1 is the mechanics of the context switch. So I'm actually giving you enough information here that you could consider writing your own real-time kernel. An operating system has a whole bunch of like utilities and stuff attached to it, but the kernel is what does the scheduling and switches between tasks and so on. And normally in this course, the 5th lab, which we don't have this time, is where students can create a game of their own choosing to run on the development board. Or for the last 3 or maybe 4 terms, I've been allowing students to write their own real-time OS instead of doing a game if they want to do that. And I might post the specification for that somewhere on Learn, just for those that are interested in it. It's not going to be something that you would submit and mark, but if anybody chooses to do that in their own time, I would be willing to answer questions and stuff like that. So, okay, so the steps for a context switch are: 1, store the execution context of the running task. So we need to be able to resume it again later. So we just save a snapshot of where it's at, and whatever task is now going to start running, we restore its execution context. So we restore the execution context of the ready task, the one that we want to start running. So we're going to look at this with the diagram. So we're going to switch from tau1 or task 1, which is running, to tau2 or task 2, which is in the ready state. So here is tau1's stack, and here is tau2's stack. And so task 1 is running, and let's just say that the stack is currently at this level. So what we would have stored on there would be the function parameters and local variables. And on top of that, I'm going to use this goldenrod color here. We have free space. And you never want to exceed the space that you have for your stack. I didn't mention that on the last page, but you saw all the stacks were close together. And so if you overrun your stack, then you're going to start interfering with other task stacks or maybe the task control block. And so you have to size the stacks. And to do that, you can run your application and you can record what the high watermark, so the operating system can let you record what the high watermark is for the stack. That's okay, I guess. It gives you how big your stack likely needs to be, but it's not a guarantee that you've seen the worst case behavior, and so it's better required to do it analytically if it's for a safety critical application. So for the switch here, task 1, we are suspending it. So we're going to push a few things. So the general purpose registers, that's R0 for the ARM, that's R0 to R14, plus the program counter, plus the program status register, and all this will go on top of the stack. That's what a push is. And we're not quite done. Before we switch to task 2, we need to record where the top of the stack now is. So this is the new top of stack here. We need to record that in the TCB. So we need to record the stack pointer, and that's register register 13, I think, on the ARM. So record the stack pointer in tau 1's task control block, or task 1's task control block. And now we can resume task 2. So what task 2 is going to look like is here we'll have the function parameters and the local variables that are for wherever it left off in execution last. And then on top of that, we have the stored context. So this was stored before, and then above that we have free space. The thing that we're going to do is, it's in the opposite order, so we will update the stack pointer from task 2's TCB, so it will now point here, top of a different stack, and then we can do the pop. So then we can pop into the general purpose registers, the program counter, and the program status register. And once we've done that, the program counter will now be pointing at the next instruction of task 2, and it can start running.